Hey, so my name is Kyle. I work for Fhenix, and I want to go over sort of some of the nuances, I guess, between using ZK for privacy for versus FHE. So kind of just like where else can we try to build it on-chain privacy, and where does kind of FHE fall into this? So real quickly, just like a quick FHE, like what is FHE? FHE is this concept called fully homomorphic encryption, which is a method of operating over an encrypted field without decrypting. So basically, you can trust that a function is going to be run correctly on specific inputs without having to know what these inputs are. So you can kind of think of it of being able to run an operation without decrypting. That's kind of like the high level summary of it. And in some ways, FHE is kind of where like ZK was sort of maybe like 3 or 4 years ago, in the sense that it's kind of still a proof of concept. There's nothing in production, but the seeds are starting to be sort of laid out. And so one of the issues with FHE over the past, I guess, few years has been the computation costs and the actual ability to do anything with it. But that is changing, and to give you guys kind of a quick summary of sort of the evolution of this technology is privacy homomorphism, I guess just the basic homomorphic encryption, has existed since the 70s and kind of broke into the mainstream in 78. But for, I would say about 30 years-ish, there wasn't really a lot of progress that was being done because homomorphic encryption uses this concept called, is something called noisy encryption, which is basically adding noise to something to try to, obfuscate the truth. So I kind of like to think about it sort of like, when you're playing poker, sometimes you got to bluff to make sure that you're not just always playing it straight up, or else people are going to know to fold when you have a good hand. But anyways, like as you can see, there's a bunch of different schemes, FHE schemes, or homomorphic schemes in general. But the big, I guess, inflection point was 2009 when this guy, Craig Gentry, came up with the concept of bootstrapping. And bootstrapping essentially is the ability to reset noise to sort of make it constant, to sort of like a checkpoint. So you can do unlimited amount of operations without having the noise overflow, I suppose. And from here, you can see that there's a lot of different variations and different schemes and forks of FHE. Specifically at Fhenix, we use TFHE, which is which is part of the fast bootstrapping branch. Again, bootstrapping is the ability to reset the noise. And we currently use a library called the TFHE RS library, if you want to look more into it, which is produced and maintained by Zama, which is an FHE research firm. And sort of like, what is the difference between FHE and ZK for privacy? I'm sure most of you are familiar with attempts to try to use ZK for privacy in general. It is sort of the standard practice and still kind of like in the zeitgeist of how to, achieve privacy on chain. But ZKPs are limited in their ability to manage a shared state, which impacts composability. Essentially sort of by keeping only the committed data and proofs of correct computation on chain. And like I said, this has issues because the plain text has to be known in order to compute it, which basically means if you want to advance a state, some level of decryption has to be done. And then from there, the arithmetic expressions, the operations can be run on whatever data was decrypted. And sort of this has definitely has its use cases, as I'm sure you're all aware of. However, it's primarily for single party compute. And yes, you can kind of bundle this compute together to sort of, kind of create creative ways of managing state, etc. But again, it does have some sort of scalability issues to some degree. But so generally speaking, but as you can see, sort of ZK and FHE are both technologies that can produce privacy. ZK obviously right now is more scalable than FHE. I mean, that hopefully will change in the future, or at least, come to some sort of more of a balance. But again, there are benefits to FHE in terms of composability, and the actual operations on state of the state can be done on chain. And in terms of scalability, I would say that FHE actually is scaling in terms of throughput, quicker than I think a lot of people are aware of. I mean, for example, something such as a ciphertext over ciphertext division was kind of thought of as impossible even as recently as like December, early 2024 in like January. But now, larger bit size, 32-bit division, multiple divisions in a transaction are feasible. If you want more information on that, we have it on our docs. But anyways, ZK and FHE are kind of solving two different problems when it comes to on-chain privacy. ZK is trying to solve the verification of like off-chain execution and then trying to verify that on-chain, while FHE is trying to solve the on-chain encrypted state privacy, but doing it on-chain. And so I think that both of these technologies together, would be ideal to use. And kind of just to summarize sort of what I've been going over in terms of the issues for ZKPs for privacy is that, again, it's difficult to compute over a shared state. And I hate saying that something can't be done because there's always a creative way to do it with trade-offs, etc. But generally speaking, I'm sure that most of you have looked at ZKP applications. At some point, a part of it does get kind of put to some sort of third party, and people will debate whether or not it's trusted or untrusted. But I am kind of speaking generally here. And again, like I said, it mostly is done off chain or client side that is the more popular nomenclature. But this can leak information to the prover, generally speaking. So in that sense, they would have to be trusted to run correctly. And to some sense, some would say that this is kind of just leading us back to square one in terms of like trust assumptions in terms of on-chain privacy. And again, like if you don't take anything else away from this talk, I guess just remember that ZKP there's not a functionality to run operations over an encrypted field without decrypting. That's kind of the main point that I'm trying to drive home here. But in all fairness, there are benefits to ZKP over FHE that need to be considered. For example, ZK allows proof of on-chain computation to be proven succinctly, which is kind of one of the benefits of ZK for scaling or, verifying that a lot of different things happen in a very short amount of time, and in terms of the small space and in small time, which does have its benefits. But I do like to think that in terms of the actual privacy methods itself, ZK can do some things, while FHE in theory can do a lot of things, pretty much everything. Hence the point of general operations for fully homomorphic encryption. However, it is slower because you actually have to run the operation. And just to really try to drive this point home, the ZK is kind of constructed off-chain while FHE does it on-chain, the operations. And since FHE can allow us to update state without decrypting, we can avoid leaking plain text to memory. And leaking plain text to memory is, one of the biggest vulnerabilities, generally speaking, in cybersecurity, just because, if it happened, if there's a trace of it somewhere on some stack, then, that's a vulnerability that a hacker could abuse. And so FHE constructs the state one step at a time, which is kind of in line with how blockchain works, generally speaking. If you think about, you have ciphertext A, ciphertext B, and that you want to run an addition operation, you can run this operation and verify that this corresponding ciphertext C will be the sum of A and B without having to know A or B or decrypt C. And so maybe for those of you that are a little bit more like visual, I kind of like the metaphor of like ZKPs are sort of like a picture. You can kind of construct all this stuff that happened off chain, verify that like, yes, this is this picture, private picture, versus FHE is kind of more like a movie or a film, which is sort of like a time series, I suppose, of frames of pictures that kind of like, for example, like an animation would show like a bird flapping its wing. But with FHE, you're actually able to have this like evolving state. If you want to append more, the bird flies up, the bird flies down. I don't know. At the end of the reel, you can add more scenes basically to this film as well. If you want to go back to, let's call it like frame 3 here, where the pebble or whatever is above its head, and you're like, that doesn't necessarily look right. Maybe it needs to be lower or something. You can go in and sort of patch it. And you can do all this over an encrypted space without having to decrypt, which again avoids leaking plain text to memory, which is ideal in terms of security. So FHE for multi-party compute. So generally speaking, the ZK private state happens off-chain, client side, whatever nomenclature you guys would prefer to use. But then these different segregated private states are sent to the validator, and then at some point, the public state is sort of the public state is constructed there. Generally speaking, a lot of times it will have to do with some sort of decryption. However, in FHE, each of the users can kind of interact directly with the validator set. And then from there, whatever needs to be public can be public, but what needs to stay private can kind of exist in this private shared state where multiple people are writing to it, etc. For example, if you think about an AMM, a lot of different transactions and operations function calls basically need to happen to this contract, right? Sometimes you need to add liquidity, remove liquidity. Multiple people want to swap A for B, B for A, etc. So there's a lot of different interactions that are necessary here. And so kind of going over alternative ways that we can kind of combine FHE and ZK to try to see where these technologies can kind of create some sort of overlap. And if anyone's curious, this is a project that was actually submitted to us last week in London at the ETH Global Hackathon. There's a QR code to the repo. It's kind of interesting if you guys want to check it out. But basically, one of our developers was able to come up with proof that you could sort of circumvent the pairing function while encrypting the result of the proof. Because generally speaking, if you know whether a proof is valid or not, yes or no, 0, 1, yay or nay, but ideally, we could even encrypt the outcome of whether the proof is valid or not as an encrypted, as a ciphertext in the form of an encrypted Boolean, which is pretty much what it sounds like. And then this can be done to verify on chain and can take action result of the proof. So basically, you can do a conditional state advancement based off of the result of the proof without having to leak the result. But this does sacrifice succinctness in terms of being able to verify the proof quickly in ZK. And so roughly speaking, this is sort of the anatomy of a ZK snark or plonk. I won't go too much into the detail here, but basically the part of the verifier that this project was kind of emphasizing is this pairing test, the yay or nay, yes or no. And so one of the ways to do this is through one of the issues with doing FHE on chain, I suppose, is the pairing function, which is very expensive to run in FHE. I mean, it's just not practical. Like I said, division is very difficult, and doing a loop of them is probably going to overflow, and it's just not really possible. And again, the main issue here is that, yes, in theory, we can use this to verify a proof, but is it really that valuable? Because we are sacrificing succinctness, which is in my opinion, arguably the main benefit of using ZKPs in general. Is that succinctness in terms of space and time. And here's just kind of another project if you guys are curious about how this can be done from the prover side. Basically using some sort of guest VM where the host will create a public and a secret key and then encrypt two numbers, so create two ciphertexts that represent the underlying value of two plaintext integers, and then pass the pub key with the two ciphertext encrypted numbers into the guest VM. And then from there, the guest VM will sort of fetch the encrypted data and initialize the framework, perform a really simple operation in this case, just like addition, and then sort of send back the encrypted sum to the host. So basically return with one specific ciphertext, and then the host can decrypt the sum with the secret key after it's done. If you guys want more information, step-by-step how this works, please check out this repo. But yeah, I do want to kind of end this presentation sort of just kind of going over my own personal, I guess, way that I sort of got into FHE. So, and I just sort of, it's pretty recent for me to learn about this too. At this point last year, I had never heard of FHE. I had no idea what it was. And I was working on a type of on-chain gaming operating system. And I realized that if I wanted to make an on-chain gaming operating system, I needed to have a decent combat engine. Right. And so from a very basic concept, I wanted to just start with something like rock, paper, scissors, right? Where if we're playing 1v1 and if I know that the other person is going to put in rock and we're playing for money, there's no way I'm not just going to query their input and then be like, okay, obviously I'm going paper. And so this can be extrapolated into something more complicated like Pokemon. I don't know if you guys are familiar with Pokemon. But, sometimes there are collisions or the interaction itself actually determines how the state is going to be advanced. And you want both players to be able to make a move without being able to know what the other player is doing. So things like protect or focus punch or dive or fly or something. I don't know. There's a lot of different interactions in Pokemon. But, going back to the example of rock, paper, scissors, basically, right, the idea is that I needed to figure out a way to encrypt the move itself. So the other person can just back run, query, and then make the move. And so I looked into ZKPs, right? Because that's the standard of let's use ZK for privacy on chain, right? That's what I thought. That's kind of the thing. And then I talked to the PSE people and eventually did some tutorials and realized that, okay, eventually it kind of comes down to like a commit reveal scheme, right? So this is kind of like sort of the process of how this would be built using ZK. And again, this is another project from one of our developers in Denver. But I think it's kind of interesting. So basically, they went over the idea of constructing a sort of rock, paper, scissors game, which is like a private, think of it like an attack looting game, which is very common in Web3, I suppose. Where basically like the defender needs to set like, okay, we're going to defend high, we're going to defend low, or defend a certain, vulnerability, etc. And then the attacker decides where they're going to go, and then the state advances that way. It's basically just rock, paper, scissors, like paper beats rock, etc. But basically, in this case, the only thing that's really committed on chain is the hash of the move. And again, this sort of just comes down to like using a commit reveal scheme, which at the end of the day, it's like if we're just going to use a commit reveal scheme, why not just use a commit reveal scheme? Although it has more interactions, and when it comes to scaling blockchain applications in general, you genuinely want to minimize the amount of interactions. That being said, this is basically sort of step one is the player is going to kind of commit to like, okay, I'm going rock, or I'm defending high or something. And then player two's attack can actually be public because, like, at that point, neither move is dependent on the other player, so you might as well just make the public attack, simple enough. And then step three, player three basically needs to reveal how they committed their move, whether it's like a nonce or sol or like some sort of pre-image, or proof. But basically, they just have to be able to verify that whatever they committed to before, if they committed to 0 before, that's what they were actually going to do. And then they can kind of determine the result of the battle that way. And then in this case, like the original player is going to kind of the second player is going to figure out like, okay, this was the result of the battle. Now I'm going to loot the city. And so as you can see, that's like kind of like 4-step process versus with that. And it requires somehow the original player to remember that their nonce value essentially. While in FHE, it's much more straightforward. Basically, the user just generates the ciphertext and passes into the function, which could be done in one step pretty easily. And so if you really think of a simple example, rock, paper, scissors, if 0 maps to rock, basically just pass in 0. And then player 2 basically just decides what they're going to do. And from there, the state can advance because, again, we can run an operation over an encrypted field without decrypting. Not the greatest example here because you actually could just decrypt immediately and no operation is happening. But I think it just goes to show that FHE is pretty good for storing encrypted fields in general. That being said, if you're interested in learning more about FHE or just building with it or just, talking about FHE or exploring the community, feel free to join the Discord or feel free to contact me directly if anyone's interested. But anyways, I appreciate it. Thank you for your time. And thank you.